Now, since I did forget to turn on the recorder before, that was our second class last time. And so I'm going to leave in the YouTube videos the second class from the last time I taught the course. Now, that's going to be near the top, if not right at the top of the YouTube videos. It's the one that says probably something similar to 5 point something to 5 point something, you know, give that. Something up until 5.3. From 5.3, I'm recording that now, so I won't keep that up, but anything before 5.3 I will leave up there. The ones from this term are at the bottom of that list. The one that said syllabus and the one for tonight, because and it'll say 5.3 through however far we get tonight. So, any questions on that? Sorry that I missed it, and try not to do that again, but remind me if you see me talking and you don't see that, you see where the cursor is there? That little circle with two blue lines in it and a number counting off here, that means we're recording. Do you see what I'm talking about? Over in the lower left corner, you see the cursor is encircling that. If you don't see that going on, say, hey, are you recording? And I'll stop and make sure that I am. All right. Now, last time we got through in 5.3 up to page 130. We're in Chapter 5, Forces, and 5.3 is Gravity and Weight. And the topic on page 130, second topic down that says mass versus weight. Okay? Now, we've already talked about this slide that's up there now, so I'm going to go to in fact, I probably will go to the next slide here. And that's on the next page. We'll get there in a minute, okay? But let's go to the blank page, and we'll start from there. And, all right. Any questions? Anything we've covered so far? Okay. Now, again, a quick review of what mass is and what weight is. Mass is how much of an object there is. How much of this stand is there here? How much of me is there here? How much of the table, the chair, whatever. It's the amount of quantity that's there. It's related to the inertia of that quantity. Okay? Now, weight, that is a force. Okay? What's creating that force? I'm standing on the earth right now, as we all are, or sitting. Okay? The earth is pulling down on us with a force. Force is a vector that's pulling downward. Mass is just how much of it is here. So you would think they weren't that much related, except that we spend just about basically our entire life on the earth. So the mass is directly related to the force, but they're completely different entities. Mass is a scalar quantity. It doesn't have a direction associated with it. How much of it there is? Force is a vector, and that is a result of the gravitational pull of whatever body you're standing on. The Earth, the Moon, Venus, yeah. I don't think any of us will be anywhere except the Earth. So that's where that is. So, as I mentioned here, an astronaut of mass 75 grams. Okay, let me get my pen set up. Okay, so the mass of this astronaut is 75, imagine it's 0.0, yeah, 0.0, not grams, kilograms. Okay, that is the mass of the astronaut. Okay, what is that astronaut's weight? What formula did we use? Previous page, 129, top of the page. What's your formula to convert mass to force due to weight? Anyone remember it? Pretty important formula. This is what we're looking for. What's the formula say again? F sub W is equal to what? mg. Mass, and this will be the mass of the astronaut, times g. Now what is g? Okay, first, what system of units are we in if we're dealing with kilograms? They're metric, more precisely the SI system, System International, okay, which is basically what we call the metric system, okay? So since we're in that system, we'll use the mass of the astronaut of 75.0 kilograms. What is G in the SI units? 9.80, is that what I heard? What units? Second, meters per second squared. Excellent. That's the acceleration due to gravity that's pulling us downward. Okay? Now, pull out your handy dandy calculators and see what 75 times 9.8 is. It's going to be something on the order of 740 or 30 something. Anybody get it? Say again? 745 or 35? 735. What units is that? Newtons, exactly. Kilogram meter per second squared is a newton. The mass of the astronaut is 75 kilograms, but the force or weight of that astronaut is 735 newtons. Okay? And that's what they got in the book. Good for them. Now, example 3 says, what if that astronaut, and this is why they chose an astronaut here, happens to land on the moon? Okay? What is his mass on the moon, or her mass on the moon? Mass doesn't change. The same quantity of astronaut on the Earth, same quantity on the moon. So guess what his quantity will be? The quantity will be 75 kilograms. How about the weight on the moon? So this will be F sub W on the moon, okay? And that will be the mass of the astronaut times G for the moon. Now they give us the moon's acceleration due to gravity. G is equal to, G on the moon is equal to 1.63 meters per second squared. Hey, look at that. It's a whole lot less than G on the Earth. Can anyone tell me a few reasons for that? The moon's mass is much, much smaller than the mass of the Earth. So therefore the gravitational attraction is far, far less. So we'll do our 75.0 kilograms. Mass is the same, but the acceleration due to gravity is much, much less, meters per second squared. So what's that astronaut's weight on the moon? Say again? 122 what? Newtons. Wow, what a great weight loss plan, huh? Just go to the moon, okay? You're bound to lose weight, okay? Unfortunately, when you come back from the moon, if you haven't lost really mass, you're going to go back up to your former weight. Does that make sense? Now 122 newtons. Okay. The astronaut's mass stays the same, but the weight varies with the celestial body on which it happens to be located. Moon is the only other celestial body that anyone has ever landed on that we know of. Okay. Earth and a few people on the moon. Now, there's another little warning here. Do not confuse mass with volume. Okay? So I think I'll go to a clean slide here. Does anyone need this any longer? Everybody got it? Okay. Now, mass is measured in typically kilograms. That's in the SI unit. No one ever measures mass in the U.S. customary unit, but this book does. What do they use for that? Slug, okay. Now, what is a volume? A volume can be represented by several different units, okay? One of these is, it's a SI unit, cubic centimeters, okay? If any of you, I think some of you do have medical backgrounds, right? If you do, maybe in the old days you heard this called cc's, okay, cubic centimeter. Better definition is centimeter cubed. Now that's not an SI unit, that's a metric unit, but the SI unit is actually meter cubed, okay? Now where do we get that? If this were a, let's say we're talking about this top slab on this thing here, its volume would be its length times its width times its thickness, okay? Length in meters or centimeters, width in centimeters or meters, and thickness, probably in centimeters, probably not meters. Then you would have so many cubic centimeters. Centimeter times centimeter times centimeter, cubic centimeter. Or a meter, the volume of this room. Meters here, meters there, meters here. Volume of the room in cubic meters, okay? Those would be, this is a metric measure, this is a SI measure, okay? Also metric. In U.S. customary, it's usually feet cubed, okay? So this would be so many feet this way, so many feet this way. That's a weird, very small number of feet this way. That would be so many cubic feet. Or the room. How many feet wide, how many feet long, how many feet high, cubic feet, okay? They don't have to be rectangular parallelepipeds like I've just been describing. Anything, the volume is measured in that. Now, a lot of time liquids will be measured in liters. That's a sort of an SI, but it's definitely a metric unit for liquid volume, okay? Any of you have a container in here with a marker on it indicating how much it is? I don't see any. Well, actually, what you got back? Oh, no, that's Madison, what's your container there? Does that have measurements on it? Oh, okay. It looked like it could. Okay. Anyway, sometimes we call a liquid volume a capacity. It's still a volume. You can convert from, and in fact, I'll tell you, a smaller unit than liter would be a milliliter. And a milliliter and a cubic centimeter are precisely the same measure. In fact, in the old days, they gave medicines by cubic centimeters. Nowadays, quite often by milliliters. Same measure, exactly the same. Okay. Now, mass is how much of an object is there. Volume is what space that takes up. Has not much to do with the mass. Okay? The astronaut walking on the moon, the mass stayed the same, so would the volume. The weight changes though. Okay? Weight and mass are directly proportional in a given place because of that formula we use. Force due to weight, that's weight is equal mass times acceleration. So as long as you're in the same place, these are proportional to each other. That is just a constant, as long as you're on the same body. Okay? So weight and mass are proportional to each other. That's why the scale at the grocery store can have pounds on the outside, a weight measurement, and kilograms on the inside, a mass measurement, because they're proportional to each other. Volume is not, okay? Volume is related to how much space it takes up. If you have, the old joke was, which weighs more, a ton of lead or a ton of feathers? Yeah, a ton is a ton. A ton of lead may be a small box. A ton of feathers may take up more than this room, you know, depending on how you pack them. They have different volumes, but they have the same mass. So don't confuse mass and volume. Later, we'll talk about a quantity that relates mass to volume, and that's a very important quantity, but I won't confuse you with it now. That finishes 5.3. Homework exercises here on page 131. I would suggest you do either 1 or 3. Those answers are in the back. They should be anyway. I would do any of the odds 5 through 9. Those answers should be in the back. And then I would do some of the odds, you choose how many and which ones, of 11 through 29, okay, to make sure you have a good, firm understanding of what's there. Answers in the back. If you can't get those answers in the back, please come and ask, okay, what am I doing wrong here, or why is this? Maybe the answers in the back's wrong. The odds are there's something that you may have missed in it. Okay. That's on page 131. All right. Next thing we're going to talk about is friction. Okay? Yeah. I'm sorry, every time I change the slides, I have to go through the same routine here. And have to get my pen back. Okay. Now, friction. Friction is a force. That's why we're covering it in this chapter. This chapter is the chapter 5 is on forces. Friction is a force that resists the relative motion of two objects in contact, this is important, in contact with each other. Okay? Caused by irregularities. My writing stinks, sorry about that. Okay, of the two surfaces. Okay. Now, that's why this figure is here. But before I go to this figure, let me do it here. Okay? I'm going to pull on the table. Now, pull is a force, right? So if I pull on the table, should I accelerate the table? You would think so. If it's an unbalanced force, there is no force against it. So I'm going to pull on it. Oh, finally I got it to move. That first bit of time I was pulling, no motion. Why not? There was friction between the feet on the table and the floor. Now this floor looks pretty slick, but actually it has microscopic irregularities. Those feet down there, I can't see what they look like, but I bet you they're pretty jagged and rough. Okay? So therefore, there are irregularities there. So this is what this is showing. Here you have a front end loader, or whatever you are, pushing against this big old block here. Now that may push with a lot of force, and it may take a lot of gas on that to finally get it to move. Okay? Now why? Okay? Because friction here between this block and that surface is resisting the motion here. Friction is a force that resists the relative motion between two objects in contact with each other caused by irregularities in the two surfaces. This surface down here has jagged irregularities, and the box on top of it has jagged irregularities. Okay? So, the force is this way, this thing pushing this way, but this is resisting the motion this way. There's another key. Frictional force always always resist the motion. So it's always in the opposite direction. Okay? Now, when I was pulling before, when I pulled just a little bit, absolutely nothing happened. That's because the friction between the feet and the floor was resisting me with just that little bit of motion. Because I only pulled a little, it only resisted a little. I pulled a little bit more, and it's still not moving, so it's resisting with a little bit more. It's sort of variable. That kind of friction is called static friction because the table's not moving. But when I finally do get it to move, then it moves a little more easily, and I'll try to explain that here. In the first case, when I was pulling and nothing happening, just picture this jag here down in this pit here. This one over here. Well, maybe move this one over here and this one over there, okay? They're down in the fix. They're fixed there, okay? That's hard to move, really hard to move. But then once you get the motion going, they kind of skim over the top, okay? And that's why you may have used to seen it in cartoons. You may have experienced in real life. You know, you push on something, can't get it to move, but when it finally moves, you almost fall down because it moves more easily once it's moving. It still has some resistance. That's kinetic friction, meaning the friction of motion. Static friction is almost always greater than kinetic friction. The stationary friction is more than the other. And here's why. Once it starts moving, then the tips sort of just glide along the top without falling into the valleys, so it's a lot easier for the motion to continue. So friction is always opposes the direction of the motion. So it's always in the opposite direction. And the static friction is usually greater than the kinetic friction. Okay. We haven't hit that yet in the book, but their figure indicated it. I want to go and say it while we had a good picture here. Okay. Now, I think I'll go on the right here since I've got this good slide here. Static friction, which I was just mentioning, and if this isn't moving, see the front end loader is trying to move, it's pushing, but this is not moving with it, so that static friction is the force that opposes the start. The start of motion. I'll make sure, yeah. Start of the relative motion. Okay, that's static friction, okay, between the two objects in contact with each other. It's sometimes called starting motion or starting friction. I seldom hear that. It's usually static friction. Now, once the touching objects are in motion relative to each other, then you have kinetic friction. What does the word kinetic mean? Moving. Have you ever heard of kinesiology? The study of motion. Okay? That's a major at UAB and probably other schools too. I know have a nephew, went to Louisiana Tech. His major was kinesiology. Later became a physical therapist. Okay? But kinetic friction is the motion once the touching objects are in motion, it sounds like it's contradictory, but it's not, of two objects once they are moving. Okay? When I pull on that table and it finally starts moving, it takes less force to keep it moving, but it's still a lot of force because I'm having to overcome kinetic friction. So the kinetic friction is the force opposing motion. Once they are moving, there's still a force that you have to overcome to keep them moving. Okay. Is friction good, bad, or indifferent? Think friction's good or friction's bad? Say again?
Either or.
Yes, you're absolutely right, either or. Okay? Now, why can I walk across the floor here? Because I have friction between my shoe and the floor. If I didn't, remember the old cartoon of stepping on the banana peel? And the legs go like this and you flop right down. No friction, you don't move. Okay? So you have to have friction. Now, in my car engine, when I was driving over today, did I want lots of friction in there? Absolutely not. That's why I have oil and everything else in there to reduce the amount of friction. However, the tires on the road, I had to have friction. Otherwise, I would have just been spinning my tires, like trying to drive over ice. Okay? So yeah, friction's good or bad, depending on where. I'm glad I'm not stepping on banana peels walking back over here. My knees already hurt. That would really send me flying. Okay. So, friction is both a necessity and a hindrance in everyday life. Another little thing, I see several people tied their shoes. Why does that work? Friction between the laces. Okay? Yeah, you make a knot, but if that was Teflon, that knot would come right undone, in no time. Okay? There is friction there. Okay? Thank goodness. Okay. Now let's see if we have the next slide here. Yes, we do. Okay? Here are a few characteristics of friction. Okay? Now, I don't have enough white space to list them all, but I'll try to do my best here. Here's the first characteristic of friction. Okay? Friction is a force. I've said this over and over. It is a force, okay? That always acts parallel to, now I'm going to put parallel lines so I don't have to spell out parallel. Parallel to the surface, okay, in contact, and opposite, I've said this before, opposite in direction. Okay, so here you are either over here pushing or over here pulling on this box, okay? If the surface is here, friction is resisting, always opposite in direction, but parallel to the surface. So the friction force is always parallel to the surface, but always resisting motion, opposite in direction to the effort force. Whether you're pushing, pulling, or whatever, friction is always operating against you. Okay, that's the first characteristic of friction. Okay? Second one, we've already stated also, static friction is greater than kinetic friction. I'm going greater than kinetic friction. Now, I've seen in several tables sometimes they're very close to equal, so I like to put greater than or equal to. The book just lists greater than. But in their table, and let me see if this table is on here. I don't think so. Okay. The table on page 133, they list static friction, kinetic friction. Wow. Steel on steel, 0.58 to 0.2. Big difference. Okay. Now these are coefficients of static friction, so we'll talk about what that means later. But look at steel on steel lubricated in the engine of my car, 0.13 to 0.13. They're the same. So that's why I like to put the equal sign there, not just greater than, but greater than or equal to. Never less than. Static friction is never less than kinetic friction, but in certain circumstances may be equal to. So we'll come to the table a little bit later. Okay, but I just wanted to point out why I say greater than or equal to, because the table said that. The book says just greater than. All right, number 3. I'm going to try to fit it down here because I'm running out of room up there. Number 3. Friction increases as the force between the surfaces increases. Whoops. Okay. Now, that's what this is showing, but let me back up one slide first. This one. Okay? Now, let's put it in the static friction initial situation where you slide this over slightly, this one's down here, that one's down there. And then you go to push on it, and you're bumping against here, you're bumping against there, all the way along here. Okay. What if you put another block on top of this? Now that pushes these down deeper into the crevices, and it's even harder to move. So that's what we mean by, okay, what I wrote here, that the friction increases as the force between the surfaces increase. Okay? Now here is an example of this. If you take your two hands and rub them gently across each other, you can feel some friction there. And you don't really notice too much. Now press down on them and rub. And what do you notice? They get hotter. Why? There's more energy it takes to do that, and you produce heat. So the friction increases as the force between the surfaces increase. That's what they're trying to show here. You have one crate here on the floor. You're pulling here. Friction force is opposing you there. This looks like static friction because these look like they're the same. But you put another crate on top, you can have to really increase the force here, and the friction force is also increased until you finally get it to move. That will be a much bigger effort force required. Friction increases as the force between the surfaces increase. Now, that goes back to, and I'm sort of jumping a rabbit here, but it is pretty important. Let me go back to this. Remember this slide? It was the last one we did, or one of the last ones we did in the last class. Okay? The weight is down. The normal force that the table pushing up on the brick, that's the normal force. Gravity's pulling down on the brick, that's the weight of the brick. The table, if it's not crushing the table is pushing up on the brick. That's its normal force. Okay? The greater the weight, the greater the normal force. So we'll see coming up in just a little bit that friction is dependent on the normal force. The perpendicular force to the surface of the table, or whatever you've got. We'll see that a little later, but that's why we mentioned normal force before. We didn't do much with it. Here's why we mentioned it. Okay. Now, let me give you a little bit of nomenclature then. Oh, here it is. We're right there. Okay. Let me try to put it in here. Here's your formula for frictional force. Okay. Any force in this book is a capital F. If it's a net force, that could have been F sub T, or total force. Normal force is F sub N. Weight is F sub W. Frictional force is F sub little f. That's the force due to friction. Okay? The force due to friction is equal to this funny looking symbol here. Anyone know what it is? A Greek letter, lowercase m, mu. Mu. That's the Greek letter mu. And that stands for the coefficient of friction. Okay? Times, like I just was talking about, the normal force. So remember I said it's related to the normal force. This is it. The greater the force that the surface is having to push up on the object, the greater the friction. Okay? So the frictional force is the coefficient of friction times the normal force. Okay. Now, when I was mentioning the table before, those were coefficients of friction. This was frictional force. Or force due to friction. It's just easier to write frictional force. And this is normal force. That was the force of the ground up on the box. Okay? That's the normal force. Okay? So to fill in here, the normal force is this way, F sub N. The weight is pulling downward here, F sub W. Usually the normal force and the weight are the same, unless, of course, the surface is giving way, and then the weight is greater than the normal force. Remember my example of putting a 1x6, 1x10 across there and me stepping on it? No, that wouldn't quite be even. Okay. Now, I'm running out of room, so I think I'll go to the other slide. Sorry about this, but okay. All right. Let's talk about that coefficient of friction. Now I got to get my pen back. Okay. The coefficient of, I think I left off a syllable in there. Coefficient of friction. Okay. Here's the definition. Is the ratio of between the frictional force, I don't like writing it that way, but that's how they're saying, between the frictional force that's your F sub little f, frictional force, and the normal force. Oops. Okay. Now, recall that formula I just showed you? F sub f, the frictional force, is equal to mu times the normal force. Okay, I think they put capital N, but it doesn't matter. Okay. Well, look. Let's divide both sides of this by the normal force. This goes out. And then the coefficient of friction, mu, is the ratio. Ratio means comparison in a division sense, the frictional force divided by the normal force. That's the ratio. That's how they define the coefficient of friction. Okay? So that statement comes right out of that formula. Okay, hand in glove. Okay, now let me go back to the table I was talking about before, and I don't want to write all these down. Probably don't even want to say them all, but not all of you have books, so just give you an idea. Steel on steel, now these are just sort of average values. Static friction, 0.58. You don't need to know these or memorize them or anything. Kinetic friction, 0.20. Wow, is static friction ever greater than kinetic friction? Steel on steel, when it's lubricated, they're almost identical. 0.13 to 0.13. Much less. The ratio is much, much less. Glass on glass, static, 0.95, kinetic, 0.40, less than half. Okay? Hardwood on hardwood, static friction, 0.40, kinetic friction, 0.25. Now, they say steel on concrete, they don't even give a value. I don't know why, but the kinetic friction, for static, kinetic friction, 0.30. Aluminum on aluminum, 1.9, and they don't give that static friction. They don't give a kinetic friction. Now, here is why I've heard that's the case. Okay. Remember before I said static friction is greater than or equal to kinetic friction. I wanted to put in there usually. Okay? And here's why I say usually. That aluminum on aluminum is exactly the type of reason. Aluminum is a very light metal, but it's also a pretty soft metal. And if you start moving aluminum over aluminum, there's a good chance that little jigs and jags down here are going to go down here and start digging into it. So you may find out that the kinetic friction appears to be even greater than static. But that's rare because of the fact that aluminum is a soft metal. So they left it off here, I think, to keep from saying we said it wrong before. They should have put a usually greater than or equal to, but they didn't put that in. Rubber on dry concrete, 2.0 static friction, 1.0 kinetic friction. Rubber on concrete. What does that sound like? Driving a car, exactly. Okay? Now, do you want your tire to have static friction with the road or kinetic friction with the road? You want to have static. If you have kinetic, you're spinning your wheels. Can you control a car if it's spinning? No. So you always, and in the old days, if you hit an oil slick, an ice slick, water slick, something like that, and you started losing control, started sliding, they say, let off the gas. So you decrease until you get back to a static friction case. Nowadays, a lot of cars have, say again, traction control, or also, in a sense, on the braking side, anti-lock brake, to keep you from locking up. So it always tries to maintain static friction, not kinetic friction. And the reason is, once you go to kinetic friction, you have way less control. It's less than half that. Now, what if that is rubber on wet concrete? The static friction goes down from 2.0 to 1.5, but so does kinetic friction, but it doesn't go down as much, 1.0 to 0.97. So if you got wet conditions on the road, slow down. Maintain that static friction. You don't want to go to kinetic friction. Then you're sliding and you have no control or less control. Aluminum on wet snow, 0.4. Static friction, kinetic friction, 0.02. Now, what in the world is aluminum on wet snow? Can you imagine who's interested in that? Downhill skiers, okay, they want that friction to be as little as possible, and that's usually kinetic friction. 0.02 is pretty small. Okay, now not all their skis are made of aluminum, but quite a few of them are. Some may be some type of fiberglass or something like that. Steel on Teflon, 0.04 static, 0.04 kinetic. Another place where they're equal, because guess what? The Teflon, what is Teflon? Does anyone know? You probably have some in your house. Coating on your pots and pans that keep things from sticking on it, reducing static friction. That is where you don't like friction. When you have to scrub that stuff off of the pan, you don't like the friction. You want it to slide off. That's why they have Teflon. Now they have some more names like Keflon and other things that may be as good or better than Teflon. All right, let's do example 1. They do have a try this activity, how you can find a coefficient. If you want to try that, you certainly can. That's not required. Okay? But to reduce kinetic friction, use smoother surfaces, use lubrication to provide a thin film between the surfaces, use Teflon to greatly reduce that. And here's the other thing. Substitute rolling friction for static friction. Okay? Now, we didn't mention rolling friction, but you see, if I wanted to move that table, I could drag it across the floor, or I could turn it upside down, or maybe leave it right side up, put it on a dolly, and it's real easy to move, because then you're substituting rolling friction. We're not dealing with rolling friction now, but it's a very nice thing to have at times. All right, let's go to, I'm pretty sure this figure is not in the other set, so I'll do it here. A force of 170 newtons, and they aren't specifying what force that is, so that's just F, of 170 newtons, and I'll put degree. What is wrong with my brain? Okay, newtons. Is needed to keep a, no, this picture isn't even right, a 530 Newton wooden box sliding on a wooden floor. Okay? What is the coefficient of kinetic friction? Rather than write it out, I'm just going to put the symbol, mu. Okay, now what things are we talking about here? What do you reckon that 530 Newton wooden box means? If I said, I'm a 210-pound person, what am I meaning? How much I weigh. This is the force due to weight. Okay? Now, this is a force necessary to keep it moving across the floor. Needed to keep it sliding on the floor. So guess what that is? That's the force you're having to pull. Whoops, I went the wrong way. Pull to overcome sliding friction. So this is going to be F sub F. That's your frictional force. Now this is kinetic, so I'm going to put F sub KF, kinetic friction. Okay? Now, if that's the kinetic friction, okay. Get back to this. So, here is the figure they show, and this is pretty reasonable. This is the floor. Okay, you're sliding across the wooden floor. Okay, here's the crate that you're pushing on with 170 newtons. And we'll just call that F sub P for push, okay? 170 newtons. Now, one thing they haven't shown here, they aren't putting any bars over the zeros. What does that mean as far as significant digits? 2 and only 2. That's 2 significant digits there, 2 there. If they had a bar over that 0, that would be 3 significant digits. They don't, that's just 2. Okay? So there, your push is 170 newtons. Now, that's to keep it sliding across the floor, and what they didn't say, at a constant speed. If it's at a constant speed, that means you're not accelerating, so you don't have any net force. That's your total force of pull, meaning that your frictional force always resists that motion, and that's also your F sub KF is also 170 newtons. That's what I was meaning, because this is what you're having to push. This is also your net, your frictional, your kinetic friction force, okay, because it is moving. Okay, now, if this is your weight, weight is always toward the center of the earth. So F sub W is 530 newtons. Now, what force have we left off here? The force that the floor is pushing up on the block. Okay? Anyone remember what that one's called? Perpendicular or normal to the plane? F sub n. The normal force, because it's not flying off or sinking into the floor, or wooden floor, I think it says, then this is also 530 newtons. Has to be. Otherwise, it'd be sinking into the floor or flying off the floor. It's not. So those two forces are equal and opposite. Okay. Now, remember what the mu was defined to be? And this happens to be kinetic friction, coefficient of kinetic friction. What was that ratio? Say again? Okay. It said the ratio of the frictional force to the normal force. So the frictional force is 170 newtons. Ratio of that to the normal force is 530 newtons. I probably should have put the formula in there first. F sub F to F sub N. Okay? And that's what we have here. So someone with your handy-dandy calculators, 17 divided by 53. I just made it easier. Say again? 0.1 more time. 3.2. And you only do 2 significant digits because these only had 2 significant digits. What units is that? No! Newtons cancel out too. It's a dimensionless quantity. The coefficient of static friction in any way is dimensionless. That's why you don't have any units listed, because it's newtons divided by newton. The units cancel out. Okay. And in the book, they got 0.32, period. Okay. No units associated. And they say underneath there, note that mu does not have a unit because the force units always cancel. If you got a frictional force in pounds and a normal force in newtons, don't even do the problem. Convert one to the other, make sure they're in the same units. And what I was mentioning before, physics connection here in your text, page 134, friction and anti-lock brakes, that goes right along with what I was saying. Okay, we finished 5.4. Homework exercises here includes any of the odds 1 through 7 and any of the odds 9 through 15. All those should be in the back of the book. Now, if you can't find it in the back of the book, don't worry, don't bother with it, but do one that is in the back of the book. This is on page 134 and 135. Now, there is another thing mentioned here called new technologies, a hydrophobic metal. It's a way you can reduce friction because the Teflon coatings have long been revered as low friction solutions for metal coatings, frying pans, things like this. The egg slides right off the pan, doesn't stick. And then they talk about some more people. I'll let you read that on your own. We're not going to actually do it. All right. Now we're moving to section 5.5. And does anyone need this left up here any longer? You okay with it? Okay. Then let me clear the screen here. I want to go check on the other. No, we're not ready for the other. 5.5 is talk about total forces in one dimension. Okay? One dimension means straight line motion. No turning, up, down, right, left, nothing like that. Straight line motion. Once you go 2 dimensions, then you could have something going up and coming down while it's moving in this direction. We're not doing that now. We're doing straight line motion, motion in one dimension. Okay? So, the little blue box here. When forces act in the same or opposite directions, same or opposite directions, that means one-dimensional motion. Okay? When those are happening, the total and the other word for it is net. Now, frankly to me, those sound like they're almost contradictory. When I think total, I think things are added together. When I think net, I think things are subtracted. Don't think in those terms. Total or net in physics means the same thing. Okay? The total or net force can be found by adding the forces that act in one direction okay, or subtracting the forces that act in the opposite direction. Okay, if they're going in the same direction, you add them. If they're going in opposite directions, you subtract them. Okay. Now, here's example 1. Okay. Now, this is the place forces are vector quantities. Good idea to draw them as directed line segments. Put the direction they're going, put the arrow in the direction they're going. Okay. 2 workers push in the same direction to the right. So we'll have the crate here. Okay. And we'll have 2 guys pushing on it. Big guy and little guy. Whoops. Okay, big guy and little guy, both pushing on the crate. Okay, the big guy's pushing with, or the little guy's pushing with 150 pounds of force, and that 0 is significant. The big guy is pushing with 175 pounds of force. All 3 digits significant there, of course. Find the net force exerted. Both pushing in the same direction. So what do? Force. Okay, so the net force. Now, what they use for net force is this Greek symbol sigma, which means the sum of the forces. Now, if they're in the same direction, you really are adding. If they're in opposite directions, the sum is one is positive, the other is negative, but you're still adding. But you're really subtracting. Okay, so the sum of the forces, or the net force, would be, what did you say? Add them together. 175 pounds plus 150 pounds. And what does that give you? 325 pounds. That's pretty simple, isn't it? Okay. But we're dealing with vectors. This is to the right, because each of them was pointing to the right. So quite often when you're dealing with vectors, you need to give direction. Not just a magnitude, 325 pounds, 325 pounds to the right, indicating it is a vector quantity. Okay. Now, this time the same 2 workers are pushing with the same amount. However, this time the motion is opposed by static frictional force of 300 pounds. Static frictional force is always opposite to the thing. So here's your F sub F, and this is, if that's opposite in direction, that's a minus 300 pounds. Okay? That would be to the left. So the frictional force is in the opposite direction. So what's your summation now? Your total force, your net force now, would be this force to the right, 325 pounds. But now your opposite or opposing force, or your frictional force, is minus 300 pounds, which gives you a net force of 25 pounds. Now, you might say, hey, wait a minute, don't I need 3 significant digits? No. You keep up with significant digits when you're multiplying or dividing. When you're adding and subtracting, you can't create a new digit like putting 25.0, because you didn't have any point zeros there. You have to keep it with the unit you're dealing with. If it's pounds, it's pounds. Not tenths of a pound or tens of pounds, it's pounds. So you have to keep it with the fundamental unit. Okay. So that's 25 pounds. What did I leave off? To the right, to the right. Perfect. Now, here's a dumb question perhaps. If it had been just the big guy pushing, what would have happened to this situation? It would not move. It doesn't come back on him then, because static friction, if he pushes with 175 and this has up to 300 pounds of frictional force, then it's only going to resist him with 175. If the little guy was pushing along, he wouldn't move either, because this would still only push back with 150 pounds. Frictional forces don't do the max, they just do what they need to keep you from moving. But this is kinetic friction here. They're pushing enough to overcome it, so the total static friction force is 300. So that you do subtract. All right. Oh man, my knee hurts. Let's do example 3. Ooh, yuck. Okay. Example 3 is this. The crate right here that they're pushing on has a mass. Now, what unit was the mass going to be if you're dealing with pounds? Say again? I couldn't hear. What unit would you use for mass? Slugs. Yuck. Who uses slugs? The mass here is 5.00 slugs. There's no abbreviation for it. If you're using it, you got to spell it out. Okay? What is the acceleration when the workers are pushing against the frictional force? So we're looking for acceleration. Now that was a few sections back, but we're still going to use it. What is the relationship between mass, net force, or your sum force, and acceleration? Anyone remember the formula? Oh, we had that a week ago. We don't need it anymore, do we? Yeah, we do. Don't need it all through the course. What's the relationship between force, net force, mass, and acceleration? Say that one more time. Excellent. Newton's second law, and this is net force. I'm going to put sum force is equal to mass times acceleration. Now we can either plug our numbers in there and then do our math, or we can rearrange the letters and then plug in the numbers and just do the math there. Which you prefer? Plug and chug or chug and plug? Want to solve for A first, or you want to plug in the numbers first? So solve for A. So what would we do to solve for A? Divide both sides by M. Perfect. So A is equal to the sum of your forces divided by your mass. What was the sum of the force for this one? 25 pounds, and you only have 2 digits there, divided by mass was 5.00 slugs. You can't abbreviate. There is no abbreviation. What does that come up to be? 5.0. You have 2 significant digits there, 3 here. You go with the lesser, 5.0. And what's the unit of acceleration in the U.S. customary system? Anyone remember? Feet per second squared. Feet per second squared. 5.0 feet per second squared. Okay? Perfect. Ready for example 4? Everybody got that one? Okay. Example 4. All right. This time, the 2 workers push in the same direction on a large pallet. Now, I think of pallets as being pretty small, so I can't imagine how they're doing it. So let's just draw it just like the crate before. It doesn't matter. So let's do just like the crate, and we'll have force by one guy is going to be 645 newtons, and the other is going to be, I put them in the wrong order, but it's okay, 755 newtons. Now, you think these are harder workers than the last one? No, these are different units. Newtons are smaller than pounds. So I don't know. They may be, but we just don't know. Okay. The force exerted by one is 645 newtons. The other is 755 newtons. The motion is opposed by a frictional force of F sub little f is always opposing 1175 newtons. Find the net force. How would you do that? Net force, the book uses sum F is what? Tell me. What would you do? Help me, somebody. I'm drowning up here. Add the 2 to the right, 645 Newton plus 755 Newton, and then subtract the 1175 Newton. Okay, I'm going to do the addition first because that's a little easier. That looks like to me to be 1400, is it? Yay or nay? Okay. Now I'm going, no, we'll just leave it like that. And then I'm going to subtract from that. I'm going to put it underneath because I like to subtract vertically rather than horizontally. 1175 newtons. What does that give me? I know that's going to be a 25, be 225 newtons. Which direction? They didn't give us directions here, but because I drew it this way, I'll put to the right. Okay. They didn't say either. They just said 225 newtons. Shame on them. Okay. That finishes 5.5. Find the net. Okay. Homework exercises here. Do any of the odds 1 through 9. And then do either 11 or 13. Okay. This is, they start on page 137 and it goes to 138. And guess what team? Would you mind, okay. I just want to see if they left the office unlocked. I wasn't anticipating finishing the chapter today. I'm going to put this on pause. Don't let me forget to. Now, 5.6, I'm going to end this and go to the other slide, other PowerPoint. All right. There are a few things I found a little unsettling about their illustrations here, but I think it's okay. All right. What they're showing here, or trying to show, is when an automobile accelerates, we know that a force is being applied to it because of Newton's second law. F is equal to ma. That automobile has a mass. If it's accelerating, there's got to be a net force acting on it. Otherwise, it wouldn't accelerate, okay? Now, a net force is being applied to it, okay? What applies this force? You might think it's the tires exerting the force on the automobile, but it's really the road exerting a force on the tire. As long as the tire's not spinning, when it's moving, the road keeps it from slipping and pushes the car forward. That's why it goes forward. Because the tire is pushing on the road, that would push it in the other direction. Okay? Now that's just a dumb distinction there, but actually what's going on, they're both happening. Okay? And this leads to Newton's third law. Okay? They don't have the slide here I need. Okay. Yuck. So, Newton's third law is, for every action, there is an equal and opposite reaction. Okay? When I walk across the floor, I'm pushing against the floor pushes against me. Me pushing against the floor, I'm not going to move the floor anywhere, okay? Oh, okay? But the floor pushes me in the direction I want to go. For every action, there's an equal and opposite reaction. I've heard that Newton expressed it this way. When I push on a rock, now this isn't a rock, that's a table, the rock pushes on me. Well, look at my finger, it was pushing on me. because my finger's indented there, okay? That's how he expressed this. This is how we think of it. For every action, there's an equal and opposite reaction. Equal meaning same magnitude, opposite meaning opposite direction, okay? Now, this figure isn't showing that. This is showing the car accelerating this way, but there's a frictional force opposing it. So the net force here would be 400 pounds, okay? But they didn't do a good job of explaining that in the picture here. There's a net force of 400 pounds in this direction. But for every action, there's an equal and opposite reaction, and they don't show the next slide, but if they did, these would have been equal and opposite. Now, here's a distinction, because it doesn't look like here. Okay. What this is net force. The road is pushing on the tire in that direction, net 500 pounds, but friction is retarding the tire at 100 pounds. Both of those are on the tire, okay? That's net force. Net force is always on the same object, okay? I stand on the floor, the gravity's pulling down on me, the floor is pushing up on me. I'm the object of both of those forces, okay? When you're talking about action-reaction or Newton's third law of force, that's I'm pushing on the table's pushing on me. Two different objects. One pushing one way, one pushing the other way. So if you were showing this in Newton's third law, the tire is pushing on the road with a net force of 400 pounds, and the road's pushing on the tire with a net force of 400 pounds. Action, reaction always are equal, but they're always on different objects, okay? So this is a net force issue here. They're both on the tire, okay? But if you did tire on the road, 400 pounds, road on tire, 400 pounds. It's two different objects, always equal and opposite. Now, they really don't have a good place to write here, so I'm going to have to get out of this and go back to my white screen here, and also get my pen back here. Okay. So, Newton's third law is the law of action and reaction. I abbreviate like crazy, okay? Okay. What this is, for every force, okay, applied by object A on object B, that's the action, okay, there is an equal, meaning same magnitude, but opposite. It means different direction, opposite direction, force on object B exerted by object B. I've got my ons and bys backwards. Whoa. On object A. Okay. That's your reaction. Okay. Now, sort of a dumb example of this, but realistic. Okay. Any of you ever been in a lightweight, say, aluminum fishing boat? Okay. Now, have you ever paddled or somehow got up to the dock and you thought your buddy was either holding or tied it up, and you went to step off of that? You exert a force on the boat exerts a force on you. You hope if it's tied up, then you can step off. But if not, you push on the boat pushes on you, it goes this way, you go splash, okay? That's because equal and opposite reaction. Now, if you got it tied up, you push on it, and it pushes you off the boat. That's fine. You don't splash then, okay? This example here, a bit more violent, okay? But true, is, have any of you ever fired a weapon? Okay, some of you have. Pistol or a rifle or both, okay? Now, if you've ever fired a weapon, let's do the pistol like they've got here. It's just bang and it goes, right? No, it's bang and it goes like this or like this. Because even though you're pushing a very little bullet out of here, the force that you're exerting on the bullet is equal to the force that the bullet and the explosion is doing on you. Now, if it's a rifle, you better have that rifle snug up against your shoulder. Have you ever not done that? Okay, good man, okay. If you don't, you have a pretty big size bruise right here, because then that rifle is kicking right back into you. If you have it snug against you, now your mass is added to the mass of the rifle, so there's a lot less kick. If it's just a rifle, it really kicks, okay? So the action on the bullet is equal and opposite to the reaction on the hand, okay? These two forces are equal and opposite, okay? And if you think about the speed at which that bullet's leaving that rifle, that pistol, that is a significant force on it. Throwing it out there at that speed, then you're going to have significant feedback here. So we'll talk, well, no, we actually aren't going to do too much there. There is another sort of interesting illustration here, and I've used it in other classes too. What was the first manned flight that you know of? I'm not talking about Kitty Hawk. Man was able to fly before Kitty Hawk and the airplane. How were they able to do it? They still do it over football games sometime. Does the word Zeppelin come to mind? Blimps, okay, dirigibles, hot air balloons, okay? So one of the first ways of flight was like a balloon. If you blow up a balloon, you've got pressure in the balloon. If you release that thing without tying it off, the end of it, the nozzle, then the balloon goes all over the place, right? Why does it go in crazy directions? Because the nozzle is floppy. So every time the nozzle points this way, it goes this way. When it flips this way, then it goes that way, because you have a floppy nozzle. Now they show in the book, if you put a straw and do it along a line like a zip line, something like that, then you keep it going in one direction. So that was the earliest flight. Action, air rushing out of the back, reaction, the balloon goes in the opposite direction. Okay? Now, the next flight was propeller plane. Okay? Kitty Hawk. Okay? And ever since then. A propeller plane, the propellers have that cant to them And so when they turn, they're pushing air backwards. That pushes the plane forward. That's how a propeller plane works. Action, reaction. Propeller pushing on plane, the air pushing on the air pushes on the plane. Okay? Then we got jets. Jets is the fuel burns and sends it out a nozzle in the back. The force due to air pushing out the back, or the gases, the exhaust pushing out the back, that's what sends the jet plane forward. Okay? And then sort of similar to that is the rocket, and that's the last big means of transportation. The again, the rocket's exhaust pushing this way, lifts the rocket that way. So always action, reaction. Every form of transportation we've got is basically based on that. All right. There are no questions in 5.6, and that does finish the chapter. Okay? Now, in your books, if you got your book, there's a glossary, which has a lot of the terms that I've tried to put definitions down for. Good thing to know. It has some formulas. Now, this is just a minimal amount. You can rearrange them, remember, in many different orders. So you have those. Then the review questions are probably good to look at. They basically get your concepts down, but your review problems, that's what the test is going to be more like. So any of the odds, 1 through 17 of your review. And then there's some applied concepts. If you're interested in looking at those, you certainly can. Now, why do I tell you about these problems? Okay? Well, number one, you can practice. Their answers are in the back of the book, the odds anyway, and you can make sure you've got the good understanding. What I'm about to give you is your test, which is going to be of problems. Now, you remember I said you always have 2 weeks to get it back to me. One reason I give you 2 weeks is so you always get to ask questions the next week. Okay? And here is a question that I will not answer to your satisfaction. Can you do number 7? Or maybe I will. I'll say, yes, I can. But I'm not going to do number 7. That's a test question. That's what you're being tested on. Okay? However, if you find one like it in the book, whether at the end of each section or at the end of the review problem, then I'll do anything that's in the book. Okay? Now, the other type question you may have is, what do you mean by this? Well, I'll try to answer that one. But can I work it or will I work it? No. That's your test question. But I will work anything from the book. So here's the test on Chapter 5. Okay? I'm pretty sure I've got enough copies. Some of these got a little wrinkle. And there is a correction on it, so let me make sure you understand the question. Correction, sorry. Okay. Does anyone here know anyone else who either left early or is in the class and hasn't shown up yet? But it's planning to. Pass 1. Pass 2. Here is the correction. Number 7. Okay, I'll just pick that out of the blue. A small railroad engine is able to exert, and what they had down there was 17,500 pounds of pulling force. And then they give the coefficient of friction for steel wheels on steel rail, just like we had in the book. How many rail cars weighing 45,000 pounds each can this engine pull on a level track? That has several features in it you're going to have to put together. But when I started grading this the first time I did it, now this is printed right off of the test bank. I didn't type it. This is what the test bank was. But when I started grading it, I was getting such weird answers that I stopped and did the problem myself. You couldn't do it. It wouldn't pull a thing. So I started working backwards from the answer and realized they left off a 0. It's 175 pounds of pulling force, not 17,500. I don't know. Like I said before, the PowerPoint sort of stink and the test bank sort of stinks. Okay? So that is a correction I did. All right. These are due in 2 weeks. Let's go on and get started on Chapter 8. Too bad we can't do Chapter 6. Great chapter, but that's not in your course description. Chapter 7, another great chapter, but not in your course description. Chapter 8, however, if I can ever get to it, is work and energy. So let me get off of this one, end it, and go to Chapter 8 here. I can't get it to pull up. Okay. Why did that come up? There we go. All right, here's Chapter 8. Now, Chapter 8's title is Work and Energy. Now, you may think, why work and energy? Work and energy are really the same quantities, okay? They're used the same units, okay? One is, work is the use of energy. Energy is the ability to do work, okay? So they're hand in glove, the same thing. And that's what this chapter is dealing with. First question here, what is work? The common idea of definition of work is quite different from your technical or physics definition, okay? And here's my dumb example on this one. I don't think I've given this before. If I have, stop me. When we moved into the house we're in now, I don't want to say a new house. My wife likes old things, thank goodness. Okay, she married me. Okay, but anyway, we moved into this house. We moved from a 1920 two-bedroom bungalow to a 1930 bigger house, and it was in a neighborhood she liked a lot better. It had a lot more trees around it. I like that. However, there was one little issue with it. It was on a hillside, and some previous owner, in those 40-some years since it had been built, had built additional rooms on the back. But it was on a hillside, so it built it into the hill. So the windows in the back were just above the soil line, and it made the house look really squatty in the back. And because it was back there, the water coming off the hill just went right against the house. Now, they used probably decent materials and stuff like that, but still over time, that water is probably going to damage, rot the wood. Probably was well-treated wood. Also, the pressure could weaken the structure. And then also, with the windows and the sills right above soil line in the south, what's an issue there? Termites. You need to have wood-to-ground separation. So I said to my wife, if we get this, we probably are going to need to do something to get the water to go away from the side of the house, but also lower the soil line so it won't be right up against the window sills. And she said, good, I wanted a patio anyway. Whoa, way bigger job than what I intended, okay? I wanted just to do a berm or something like that. She decided she wanted a patio. What we did to outline the patio, she took a hose and laid it on the ground. Let's build it out to here. Oh, that's a lot of digging. How I overcame that, I encouraged her to help me. So then the hose got moved in closer. Okay, so now, the other thing, if you've ever done any digging in this area, any major digging, you're going to hit rock, okay? And we were right over at the base of Red Mountain, and there were rock, And it happened to be, as I was digging, I would hit rock. And most of the time I could dig around them and get them out. But when I was right around the middle of that patio area, I hit this rock that just kept growing. Deeper, deeper, bigger and bigger. And finally I got to the level I was going to stop, but I couldn't move that rock. Okay. So I was out there prying and pushing and pulling and doing everything I could, sweating bullets in the summertime. Was I doing work? I would have thought so, but in physics definition, no, I wasn't. Work involves motion. I could yank and grunt and sweat and do everything, but if I didn't move that rock, I wasn't doing any work on the rock. So that's the difference between everyday use of work and the physics definition, the technical definition. Okay. Now, should have saved that for later, but let's see if they have this figure here. No, not quite. Okay. In fact, that figure is pages away. There it is. Okay, so let's go back to this one and go from current slide and get my pen back. Okay. I can't draw this very well, but here's a crate, here's a crate. Okay? This guy here is pushing like crazy on the crate, but it's not moving it. How much work is he doing? Zero. Even though he's pushing and grunting and everything else, doing no work. This over here, if he's able to get it to move, yes, he's doing work. Okay? Here is the physics definition for work. Okay? Physical definition of work is even narrower than what you would think. Work is the product of the force, I can't write, in the direction of the motion. Okay? And the magnitude, I don't like the way they're phrasing this, of the displacement. Okay. So, to narrow that down to an equation, here's what you got. Work, capital W stands for work, okay? Work is equal to force, capital F is force, and then your displacement. I like to use D or X or something. The book likes S. So S means displacement. I don't know why they use S. There is sort of a reason, but we're not using that now. But anyway, that's their definition. Work is equal to force times displacement. Now, there are a few weasel words in here that you have to pay attention to. Okay? The one is this prepositional phrase, in the direction of the motion. Okay? Now, okay, I'm pulling on the chair. And what's the chair doing? It's coming this way. But I'm pulling this way. So the work that's being done is my force, not my total force here, but only the force in the direction of the motion. Remember, force is a vector quantity. So this force has a component parallel to the floor and perpendicular to the floor. This perpendicular is doing no work on the chair. Only the parallel to the motion is doing work. So that's a little caveat. If you're pulling or pushing at an angle, it's only the component in the direction of motion that's doing work. Okay? This guy pushing on the crate and it moves, then the product of his force times the distance moved in the direction of the motion, that's the work done. This one, pushing maybe even harder, maybe a greater force here, but if there's no displacement, there is no work because it's times the magnitude of displacement. If it's not moved, there is no displacement. Okay. Now, what are the units for work then? Okay. What's our unit for work? We have two of them we've been using mostly. What are they? I mean force. Units for force, huh? Newton and pound. Newton in the SI units, pounds in the U.S. customary. Okay. What about displacement in the SI unit? What is our basic unit for displacement? Say again? Meter. Okay. So a Newton meter. And what is our basic unit for displacement in the U.S. customary? Foot. Okay. Now, this Newton meter has a special name. That is a joule. Now, why did I capitalize the J? Named after James Prescott Joule. Okay? And he's featured on page 203. Okay? Incredible story on him. He was a very sickly child, but a very, very bright child. His father was, back at the time when England was still basically a feudal type system, moved a little beyond that. The rich aristocracy, they had all the power. You had to own big estates and have people under you and stuff. But this was about the time of the Industrial Revolution, was just getting started. So now we had a merchant class forming. They didn't have any power, but they began accumulating wealth. And one of the classes that accumulated a lot of wealth was the brewers. Those people who made the beers and the wines and the liquors and the alcohol. They always had a market, and they started making money. Well, his dad, James Prescott Joule's dad, was a brewer, and he became fairly wealthy. So he could afford to hire tutors, really expensive or very prominent tutors, to come in and tutor his son. So even though his son was not considered aristocracy, his son was soon beating the rich kids in science and math like crazy. Okay? He still wasn't going to be recognized by the Royal Society, except he got a patron whose name was William Thompson, who was Lord Kelvin. He said, look at this guy's work, you've got to invite him in. So sure enough, he did. Now, one of the suppositions I've heard that possibly the reason he was such a sickly child, he may have been a hemophiliac. So he couldn't get out and play or do other things, because if he ever got a scratch, he might bleed to death. So it was a pretty serious thing. But he was one bright guy. They named the joule, the unit of work and energy, after him. Now, guess what the unit is in the U.S. customary system? It doesn't have a special name. We usually call it foot-pound, okay? We just reverse the order and say foot-pound. Now, I would guess mostly you guys, but possibly you gals, have you ever used a wrench that was measured in foot-pounds? You have? What did you call that wrench? Ever hear the name of a torque wrench? Yeah, huh? Okay. That foot-pounds is not the same as work. That's torque. Because force is a vector quantity, displacement is a vector quantity, and there's two ways that you can multiply vectors. One way is called a dot product, and there you only multiply the components in the same direction. That gives you a scalar quantity. Work is a scalar quantity, whether it's joules or foot-pounds. It's not a vector quantity. But a torque wrench, your force is in this direction, but the displacement is in that direction. They're perpendicular to each other. That produces torque. Torque is a vector quantity. That's a cross product as opposed to a dot product. Now, you don't need to know that, but just so you can distinguish, not assume that that wrench is measured in foot-pounds is measuring work. No, it's measuring torque, which is a vector quantity. Still, force times displacement. One's parallel, one's perpendicular. Okay. If you've ever watched an engine rev when your hood's up, the engine is doing like this because the motor mounts are holding it in there, but it's trying to twist its way because of torque out of the engine block. Okay. Now, so those are the two units. We will start next time with example 1. I see that some of you are a little anxious to leave. All right. Now remember, I'll save tonight's class, but I'll leave in there the one from last term that we missed last week. I'm sorry, I can't hear. Okay. You know, you can rent the book. You don't have to buy it.
I know that, but financial cost.
Okay. The only thing I can think of is maybe take pictures of it on your phone, because it's going to be hard to get this without without doing the exercises.
Yeah.
Okay.
All right then.
So maybe all you want is pictures of, because you got not everything that's in the book, but most of it. So you may only want to take pictures of the homework exercises.
Okay.
So, yeah. Do you have a friend you can get that from?
I'll find somebody.
Okay. Yeah.
So I just want to make sure, would it change from like 17,500 pounds to 175?
Yeah, that, it's not 17,000. 175 is, I wrote it there.
Oh.
And I slashed my zero, so it's 175,000 pounds. That's the force of the engine, not 17,500. That wouldn't pull it.
So you said earlier 175. So which one is it?
That's what I've written there.
Yeah.
175,000 pounds. Right. Yeah.
Hi. So do you just want us to write all of our work on a different sheet of paper?
You can use scratch work if you want to. You can flip it over and you write on the back too. Anywhere you want to.
Okay.
Yeah.
I was make sure it's okay if I use different sheets of paper.
Yeah, it's perfectly fine. In fact, I encourage it because if I can see your work, I might be able to give partial credit if you don't have the right answer.
That way, so.
Yeah, you can tell I'm really big on neatness. No, I'm just kidding. Okay. Okay, good
Thank
deal.
you.
Glad you are. No, those are completely practice so you can be able to do your test.
Okay.
Yeah.
All right.